Good morning. I am Devasena. In this lecture, we are going to discuss about transfer function of armature control DC motor. This topic is present in the subject control systems. The speed of the DC motor is directly proportional to armature voltage and inversely proportional to flux in field winding. In armature controlled DC motor, the desired speed is obtained by varying the armature voltage. This speed control system is an electromechanical system. The electrical system consists of the armature and the field circuit, but for analysis purpose only the armature circuit is considered because the field is excited by a constant voltage. The mechanical system consists of the rotating part of the motor and load is connected to the shaft of the motor. The armature controlled DC motor is shown below. This is the diagram for the armature controlled DC motor. In this diagram, the field is excited by the constant voltage V suffix F and the input is applied to the armature of the DC motor. The load is connected to the shaft of the DC motor. This is indicated in this diagram. Let R suffix A is equal to armature resistance ohms. L suffix A is the armature inductance H. I suffix A is the armature current amps A. V suffix A is the armature voltage capital V. E suffix B is the back EMF capital V. K suffix T is the torque constant Newton meter per amps. The torque T developed by motor N Newton meter unit. Theta is the angular displacement of the shaft, its unit is radian. J is the moment of inertia of the motor under load, its unit is kg meter square per radian. B is the frictional coefficient of motor under load, its unit is Newton meter per radian per second, and K suffix B is the back EMF constant V divided by radians per second. The equivalent circuit of armature is shown in figure below. This is the representation for the armature portion of the DC motor. In this, the current I suffix A is flowing to that resistance R suffix A and inductance L suffix A and the back EMF. Okay. The voltage V suffix A is applied between these 2 points. By Kirchhoff's voltage law, we can write I suffix A into R suffix A plus L suffix A di A of t by dt plus EB is equal to V suffix A. That is the voltage drop across the resistance plus voltage drop across the inductance plus back EMF is equal to the applied voltage V suffix A. Consider this as equation 1. The torque of the DC motor is proportional to the product of flux and current. Since flux is constant in this system, therefore the torque is proportional to the armature current I suffix A alone. That is, torque T is directly proportional to I suffix A. Therefore, the torque capital T is equal to K suffix T into IA. Consider this as equation 2. The mechanical system of the motor is shown below. This is the mechanical part of the DC motor. This portion comprises of that inertia J as well as the dashpot B. The differential equation governing this mechanical system of the motor is given by J d square theta divided by dt square plus B d theta by dt, that is equal to T. Consider this as equation 3. The back EMF of DC machine is proportional to speed, that is angular velocity of the shaft. Therefore, E suffix B is directly proportional to d theta by dt, or the back EMF E suffix B is equal to K suffix B d theta by dt. Consider this as equation 4. The Laplace transform of various time domain signals involved in this system are shown below. Laplace transform of the armature voltage V suffix A is equal to capital V suffix A of S. Laplace transform of E suffix B is capital E suffix B of S. Laplace transform of torque T is equal to capital T of S. Laplace transform of armature current I suffix A is equal to I suffix A of S. And Laplace transform of the angular displacement theta is equal to theta of S. The differential equations governing the armature controlled DC motor speed control system are I suffix A R suffix A plus L suffix A di suffix A by dt plus EB, that is equal to V suffix A. This is our equation 1. T is equal to K suffix T into IA. This is our equation 2. J d square theta by dt square plus B d theta by dt, that is equal to capital T. This is our equation 3. And E suffix B is equal to K suffix B d theta by dt. This is our equation 4. Taking Laplace transform of the above equations with zero initial conditions, we get I suffix A of S R A plus L suffix A S I suffix A of S plus E suffix B of S, that is equal to V suffix A of S. Consider this is equation 5. That is, if we take the Laplace transform of equation 1 means we get the equation 5. And T of S is equal to K suffix T I A of S. This is equation 6. That is, if we take the Laplace transform of equation 2 means we get the equation 6. T of S is equal to K suffix T I A of S. And J S square theta of S plus B S theta of S, that is equal to T of S. This is equation 7. And this is, if we take the Laplace transform of equation 3 means we get equation 7. And E suffix B of S is equal to K suffix B S theta of S. This is equation 8. We have taken the Laplace transform of equation 4. Equating equation 6 and equation 7, we get K suffix T IA of S, that is equal to J S square theta of S plus B S theta of S. That is, IA of S is equal to, if we take theta of S as common in that other side means we get theta of S into J S square plus B S divided by K suffix T. Consider this as equation 9. The equation 5 can be written as, if we take the IA of S term common means we get IA of S open bracket RA plus SLA close bracket plus E suffix B of S, that is equal to VA of S. Consider this as equation 10. Substituting for E suffix B of S and I suffix A of S from equation 8 and equation 9 in equation 10, the equation 10 becomes, substituting the value of IA of S and EB of S in equation 10, the equation 10 becomes j square plus bs theta of s divided by k suffix t close the bracket into ra plus s into la close the bracket plus k suffix b s theta of s that is equal to va of s. That is, if we further simplify the above equation means we get r suffix a plus sla into j square plus bs plus kt kb s the whole divided by kt into theta of s that is equal to va of s. So the required transfer function is theta of s by v suffix a of s. Therefore, theta of s by v suffix a of s is equal to kt divided by ra plus sla into j square plus bs plus kt kb s. Consider this as equation 11. Equation 11. Simplifying equation 11, we get theta of s by v suffix a of s that is equal to k suffix t divided by r suffix a j square plus r suffix a bs plus l suffix a j s cube plus l suffix a b square plus kt kb s. If we further simplify the above equation, that is taking s as common and combining the s terms and the constant term, we get theta of s divided by v suffix a of s is equal to kt the whole divided by s into open bracket s l suffix a j square plus open bracket r a j plus l a b close the bracket into s plus open bracket r suffix a b plus k suffix t k suffix b close the bracket, close the main bracket. And if we further simplify this equation, that is taking the coefficient of s square term l suffix a into j in the denominator to the numerator means we get theta of s by v suffix a of s is equal to, in the numerator we get k suffix t divided by j l a, and in the denominator we have simplified the denominator term of the above equation, so we get s into open bracket s square plus open bracket jra plus bla divided by jle close the bracket into s plus r suffix a b plus kt kb divided by jle close the bracket, close the bracket. Consider this as equation 12. Equation 12 represents the transfer function of the armature controlled DC motor. That is, the Laplace transform of the output variable by the Laplace transform of the input variable. For the armature controlled DC motor, the transfer function is obtained by theta of s divided by v suffix a of s. This is indicated in equation 12. The transfer function of armature controlled DC motor can be expressed in another standard form as shown below. From equation 12, we get theta of s divided by v suffix a of s that is equal to k suffix t the whole divided by r open bracket ra plus sla close bracket into open bracket j square plus bs close bracket plus kt kb s. That is, theta of s divided by v suffix a of s is equal to k suffix t the whole divided by, in the denominator we have taken r suffix a term and bs term as common, and we simplify the denominator term, that is r suffix a into open bracket 1 plus s LA divided by RA close bracket into BS open bracket 1 plus JS square divided by BS close bracket plus K suffix T K suffix B S, that is theta of s divided by V suffix A of s is equal to, in the numerator we are getting K suffix T divided by RA into B close the bracket, the whole divided by, we have taken S as common in all the three terms. So S into open bracket RA into 1 plus STA BS into 1 plus STM close the bracket plus KT KB divided by RAB. Consider this as equation 13, where T suffix A, that is equal to LA divided by R suffix A. This is the electrical time constant. T suffix M is equal to J divided by B. This is the mechanical time constant. So the equation 13 represents the standard form of the transfer function of the armature controlled DC motor. In this armature controlled DC motor, the input variable is the armature voltage V suffix A, and the output variable is the angular displacement. That is, the transfer function of the armature controlled DC motor is the Laplace transform of the output variable theta of s divided by Laplace transform of the input variable V suffix A of s. That is, theta of s divided by V suffix A of s is indicated in equation 13. This is the required transfer function of armature controlled DC motor. Thank you very much for listening this lecture. If you like this lecture, means kindly share this video to your friends and kindly subscribe this channel.